Okay, this is the second video for this week. We're going to talk about how knowing the derivatives can help us uh, understand the shape of a graph. Okay, so this is kind of the first result. First thing is that if f prime of x is bigger than 0 on an interval, if it's always bigger than 0 on an interval, then that means the function is increasing on the interval. So again, this is why we do calculus, is that knowing something about f prime tell us something about f of x. So in this case, if f prime is, if the slope of the tangent line is always positive, then it's increasing. If f prime is always negative on an interval, then in that interval, f is decreasing. And so here's a kind of a simple example. Here's f of x, right? Let's say that we don't have a calculator and we can't graph it, but we want to know the basic shape of this graph. We want to know when is the function increasing, when is it decreasing. So first we find the f prime. So you differentiate with the power rule. So 12x to the cube, again, bring down the 4 minus 1. So you differentiate it, you factor it out. So there's a common factor here of a 12x. Take everything out, and then you can do some FOIL factor. But you factor this out, and you want to know, well, if I know if f prime is positive, then we know that f is increasing. If f prime is negative, it's decreasing. So to do that, we should figure out when f prime is 0. Again, we try to figure out basically the critical numbers. Because if I know when is 0, that can help me figure out when is positive and when is negative. So solving for 0 first, you get 0, 2, and then negative 1. So you make a number line. Notice at the bottom here, I make a number line of all the critical numbers. These are the places where f prime is 0. Now if I know where they're 0, then I can plug in points between them and try to figure out whether where f prime is positive or negative. And the nice thing is that I only have to pick one number in the interval between these critical numbers. If I pick a number here and I get a positive, then f prime is positive throughout. And the reason because is if f prime here was positive and it was negative, it would have to go to 0, but that's not possible because we've already found the 0. So again, I figure out when f prime is 0. You find all the critical numbers, and you pick one point in each of these interval and see what happened to f prime. Whatever the value is at that one point will tell you what the value is of f prime in the whole interval. And so if we do that, we get the following. We get, so again, you plug in some points between them and you get, so let's actually go back here. So let's see, oh yeah. So if you pick a point that is, say on the left side of -1, say -5 or something, and you plug it in into each of these terms, notice we're going to plug into the factor form on the right here. We don't, all you care about is whether it's positive or negative. So you plug in -5 into this, plug in -5 will give you a negative. -5 here will give you a negative. -5 here will give you negative. So negative times a negative times a negative is a negative. So f prime is negative there. So that means f is decreasing. Again, if f prime is negative, then f is decreasing. How about between -1 and 0? So say like -1/2. If you are between -1 and 0, then this is negative. Again, if you're between -1 and 0, this will also be negative. And this would be positive. Again, if you are between here and here, this would be positive. So say again, -1/2, this would be positive. So negative, negative, positive, that means the whole thing is positive. So that means the function is increasing. The function is increasing in this interval. So you keep doing this and you get that, you can get the behavior of the function, right, whether it's decreasing or increasing in those interval. And you can check that on with the calculator that it does work. So the function here is decreasing, increasing, and then decreasing and then increasing. So exactly what we predicted. Okay, so the next thing is the test is called the first derivative test. So it says that if you have a critical number and f prime changes from positive to negative, then f must be a local maximum. If it changes from negative to positive, it must be a local minimum. And if it's the same sign, if it's either both positive or both negative, then it's neither a local max or a local minimum. So that's kind of, I think the best way to see this is to some graphs. So again, right, so here C is a critical number, right, either f prime is 0 or undefined. And notice that if on the left, f prime here is positive, on the right, f prime is negative. So that means that the function is increasing and then decreasing. So that means C must be a local maximum. That's case A here. But if you have a critical number and on the left side f prime is negative, that means the function is decreasing. On the right side f prime is positive, that means the function is increasing. So that must be a local minimum. So it's easy to kind of draw pictures and kind of verify this. But here is critical number. Again, f prime is 0. But notice on the left, f prime is positive. And on the right, f prime is also positive. So there's the same sign. So that means that this is neither local max or local minimum. Same thing here. If it's a critical number, but f prime is negative and negative before and after, both same sign, both negative, then it's neither max or min. So this test will help us find local max and local min. It's a very useful test. Okay, so let's go back to the previous example we did earlier. And we can see what happens. So earlier we found out that is notice is decreasing and then increasing. So decreasing and then increasing. That means it's a local minimum. And then if it's increasing and then decreasing, then it's a local maximum, right? So notice that we can kind of figure out whether it's local max, local min by the behavior of f prime before and after the critical number. Okay, so f prime tell you whether the function is increasing, decreasing. How about f double prime? So this is a little bit more subtle. Okay, so for example, notice that f prime does not distinguish these two behavior. F prime here is f prime actually is always positive, right? The tangent line is always have positive slope, so the function is always increasing. Here, f prime is also always positive. Look at the tangent line; it's always have positive slope, so the function is also increasing. So notice that we can't distinguish both these cases. All we can say from f prime is that the function is increasing. But notice that these two function, the function is increasing differently. So for example, on the left side, the function is increasing, but but it actually keep increasing faster and faster. On the right side, it's increasing, but it's actually kind of slowing down. As you go up, it's slowing down. It's not increasing as fast. So these two have different behavior that f prime cannot see, but f double prime can help us distinguish these two cases. So let's see how. So they have to do something called concavity. There's something called concave up, concave down, and that would distinguish these two cases. On the left side is concave up. And how can you tell? What does that mean to be concave up? It means that look at f prime here. It's positive. In fact, all of these cases are positive. But notice that the slope is getting more and more positive. So small positive, bigger positive. So if f prime is increasing, f prime here is increasing, then the function is concave up. That means it's increasing faster and faster. But notice here, f prime is positive, but less positive. So it's getting smaller and smaller. So that's how you can distinguish concave down. Another way to distinguish it is to look at and this is what the text says, is that to look at where the curve is relative to the tangents. Notice on the left, the curve is above the tangent lines. So that's concave up. On the right, the curve is below the tangent lines. So that's concave down. That's another way to define concavity. So that's it. That's the definition. If f lies above all of the tangent lines on the interval, then f is concave up. If the graph f lies below all the tangent line, then it's concave down. So here it is, right? Look at tangent line. The function is always below the tangent lines, so concave down. Also concave down, right? So again, look at tangent lines. This is what's tricky here. Look at B. B is actually a place where things changes. Again, if I look at tangent lines, right, the curve is below. But notice from B to C, the graph is above the tangent line again. So B here has a kind of a change here. You go from concave down to concave up. So the way you think about concave up and concave down is the concave down is basically imagining a cup that is pointing down. That's concave down. And here the cup is pointing up, right? That's concave up. So notice that concave up, the function is decreasing, concave up. The function can also be increasing and concave up. So it has nothing to do with increasing and decreasing. It's just how the function is curving. This is concave down, this is concave up, this is also concave up, and this is concave down. So you have kind of a sense for how it looks. So here's our concavity test. If f double prime is positive on the interval, then it's concave up. If f double prime is negative, it's concave down. So the second derivative tells you about concavity. We saw this point earlier, this point B, and also C. That's called an inflection point. It's where the concavity changes from, for example, down to up. Or here, up and then to down. So where concavity changes is where you have inflection point. Here, same thing. This is also, D is also an inflection point. Concave down and then concave up. So a point is an inflection point if it's continuous and the curve changes from concave upward to concave down, or from concave down to concave up. So when you have a change in concavity, and the point is in the domain, is continuous, then it's an inflection point. This is the second derivative test. It actually kind of tells you something similar to the first derivative test, but sometimes if you have the second derivative, it can be a quick check. If f prime double prime is continuous around C, and f prime of C is 0, so you have a critical number, and f prime of f double prime of C is positive, then it's the local minimum. The reason is because you have a critical number, and f double prime being positive means concave up. So if it's concave up, then you have a local minimum. But if f double prime is if negative, which is concave down, follow my mouse here, concave down means you have a local maximum. So here's an example. I think So let's find concavity and inflection points and maximum minimum. So you find f prime, right? You factor, you want to solve for 0. You find the critical numbers. So it happens. The critical numbers happen at 0 and 3. You find f double prime. So that tells you where it's increasing, decreasing, maybe local max, local min. F double prime, you differentiate this again. That will tell you more about concavity. In fact, if you have these critical number and you do the second derivative test, you plug into f double prime. And this f double prime of C being positive means that is concave up. So that's going to be a local minimum. So f of C negative 27 is a local minimum. If f double prime is 0, then the second derivative test tells you nothing. It doesn't give you any information. We can also look at the number line as we did earlier. So again, the textbook here uses a table, but I recommend using a number line, and you plug in points, right, before between the critical numbers between 0 and 3. You want to know whether f prime is positive or negative. And remember, if f prime is negative, then it's decreasing. If f prime is positive, then it's is increasing. Let's see. And then if you plug in to find concavity, you have to figure out where f double prime is 0. So if you solve for f double prime being 0, you have 0 or 2, and then we can do another number line. You plug in points between them into f double prime, and now f double prime being positive means concave up, being negative means concave down, and if it's positive is concave up. And so notice that because we know that something about the increasing, decreasing, concave up, concave down, we can plot a fairly accurate picture of the graph. So notice here concave up, concave down. Notice here there's a change in concavity here at 2, right? And notice because you go from concave down to concave up. So we have some inflection points here, right? So there's an inflection point here. There's also an inflection point here as well. It's concave up, concave down. There's also an inflection point. Actually, this is concave up all the way. So those are the only 2 inflection points. Okay. So again, because we know. So f prime tells you something about increasing, decreasing. F double prime tells you something about concavity. Together, along with some of the pre-calculus you learn, we can draw a very good picture of the function. So this won't be tested in this course, in this summer course. So if you want to look at this, you can. But I'm gonna kind of skip through it. But I'll point out a couple of things. Basically, before we use calculus, you kind of use pre-calculus to kind of graph. You look at the domain, look at maybe for x-intercept or y-intercepts. Is there any symmetry? Is the function even? Right? Is it symmetric around the y-axis? Is it odd? So some of the pre-calculus work can help us have a picture, an idea of what the function looks like. Does it have any horizontal asymptote? We talked about limits a few weeks ago. And then we use calculus to know whether the function is increasing and decreasing by using f prime. And we can use that to find local max, local min. We can look at concavity, inflection points, and then all that will help us plot a picture of a graph. So again, if you want to look at this, you can, but we won't. I won't touch you on this stuff because it's a somewhat short course. Okay, and then the last topic is optimization for this week. This is kind of one of the most important applications of calculus. Being to optimize something, minimize cost, maximize profit, etc. So here's a kind of a classical example. Let's say that we want to do a rectangular fence for cows to kind of graze or play in. And so you have a farmer who has 2,400 feet of fencing. And he wants to build a rectangular fence. One of the borders is a river, so along the river you don't need a fence. So the question is, if the farmer has this limited amount of fencing, but he want to maximize the rectangle so that it has the most area for the cows to play in, how does he go about doing that? So let me kind of give you some picture of what this may look like. So notice that he only have a finite amount of resources, a fixed amount, 2,400 feet of fencing. So he has actually many possibilities, right? He can do 100 like this on either side. That's 200, and then 2,200. So that fence, right, has a perimeter of 2,400 feet of fencing. And the area of that rectangle, right, is 100 times 2200. That's 220,000 square feet. So that's one possibility. Notice the river is a border. You don't have to fence along the river. But notice that it turns out that that's actually not a good way to fence, right? Because you can actually, that's a long play area, but it's not very, doesn't have it's going to be small. Here's a better one. What if I do 700, that's 1400, and then 1000. Again, you add them together, that's 2400. But notice this area is much bigger. It's 700,000 square feet, much bigger than this one. And if I do the other way, if I do kind of a long the other way, then I notice that my area goes down again. So these two cases, the area is small. Somewhere in the middle, the area is better. But the question is that how do you find the one that's the biggest? We can't just try every possibility because there's infinite possibilities here, right? You can divide these up into decimal values, etc. So this is a calculus problem. We want to optimize this. We have a fixed amounts of fencing, but we want to maximize the area. So the way you do this is kind of draw a picture of the rectangle. So let's call this x. Notice these are both x's. This is the same, and this is y. So you want to maximize the area. So the thing we try to maximize is the area. So area is x times y. So the first thing is draw a picture, and come up with an equation that can connect the picture, all the variables of the picture. That's the area formula. Notice this area involves actually two variables, x and y. But x and y are related, right? Because, for example, right, if I make this 100 and this 100, then this has to be 2200. So these are, you cannot make this whatever you want. These are kind of these depend on each other. There's a relationship. So that means that these are not independent; these are dependent, and we can just and the relationship between them can help us eliminate one of the variables. If we figure out how they're related, we can eliminate one of the variables. In fact, this is how they're related. The perimeter, the 2400 square feet, tells you how x and y must be related. 2x plus y, the perimeter has to be 2400. So we found a relationship between x and y. This relationship can help us eliminate one of the variables, right? Solve for one and then plug it in to help us eliminate one of the variables. So let's do that. Let's solve for y and then plug it in. So solve for y. So y is 2400 minus 2x. Plug it into here. And now my area equation only involves the x variable. And now we notice that x has the maximum of 1200. Let's see why. The most this could be is 1200. Because right, 1200 plus 1200 is already 2400. So x has a maximum of 1200. And x also has a minimum of 0, right? The smallest this could be is 0. So because there's a maximum and there's a minimum, we have a continuous function on a closed interval. Notice we can use the method to find the absolute maximum, absolute minimum earlier. The extreme value theorem guarantees that we have an absolute maximum and an absolute minimum, and we actually even figure out a way to find the absolute maximum and absolute minimum. We said that the way you find them is you find critical numbers and also check the endpoints. The absolute maximum and the absolute minimum must come from either a critical number or an endpoint. So we find the critical number, differentiate, solve for 0. So this is the only critical number. That's the minimum number. And then there's also the endpoints. So you have to check the area for the critical number and the endpoints. So you plug in 0, the endpoint. Remember the endpoint is 0 or 1200. If x is 0, then the area is 0. If x is 1200, the area is 0. Those are the right. If this is 0, there's a whole line here that's 0. Whereas if y is 0, then the area is 0. So those are the cases where there's 0, and so those are the absolute minimum. And notice when you plug in 600, 720,000, which is even bigger than the case we had earlier of 700,000. And that theorem guarantee that that this is the absolute maximum. Let's do one more example. So that was an example of maximizing area. This is an example of minimizing something. I want to minimize the cost. I want to create a can that hold 1 liter of oil, and I want to find the dimension that can hold that can carry that capacity, but we want to minimize the cost. We want to minimize the material that's needed to construct that can. So here's the cylinder. The height is h, the radius is r. Notice that the material is consists of the top and the bottom, and then the sides. And if I were to cut vertically and unroll it, turn out that this is actually just a rectangle. The area is just h times 2 pi r. So the total area of the can is just the area of the two circle, right? Pi r squared and 2 pi r squared, plus the 2 pi r h, the area of this rectangle. So that's what this is. So again, we always try to find an equation of what are we trying to maximize or minimize. So we try to maximize area. We try to minimize the cost. We try to minimize the area. So here's the equation that tells you the area. Again, just like before, there's two variables, r and h, but they're not independent. They're related, right? If I know r, then I must know h. Because it has to hold a certain volume. And so turn out that one liter is 1,000 cubic centimeter. And so the volume pi r squared h, the volume of this can here must be 1,000. So that's give us a relationship between r and h. So if I solve for one of them, I can eliminate one of the variables, just like before. So let's solve for h, it's a little bit easier, and plug it back in for h here, and then you simplify, you get this. So now we use calculus to find the maximum and minimum. So again, as before, right, we have to kind of find the critical numbers. So you differentiate it here. Use the power rule. And then combine the fraction to one term. And to find the critical numbers, we need the top to be 0. Right? The slope has to be 0. And so you solve for 0, you get that r is this expression right here. It's a cubic of 500 over pi. And then we can use that process we found earlier. We can check that, for example, before this critical point, the slope is negative, which means it's decreasing. And after this point, the slope is positive, so it's increasing. So you can use the first derivative test to know that it's the local minimum, right? Because before it's decreasing, after it's increasing. So this is the local minimum. But this is the only critical number, so it must also be the absolute minimum as well. One thing I'll point out is that this looks kind of messy, but if you plug it back in, you can see that with this r, h gives you, again, with some algebra you can check if you want, h is actually 2r. So the can that minimize, again, the can that minimize the cost, minimize the area, holds the same amount, is the can that is kind of a square can, right? Where the height is 2 times the radius. You know, where the height is the same as the diameter. And that makes sense, right? It's kind of you want to maximize something, you want to make it kind of like as square as possible. You don't want it to be too long, right? Or too, you don't want it to be super long like a Red Bull, right? Because that's not as efficient. If you have those long can, you don't want it to be so flat like a pancake. That's not efficient either. So that the one in the middle is the most efficient, the square one. And so, and this shows that the height must be 2 times the radius. The diameter and the height must be the same for this to be cost minimizing. Okay, and so the idea of optimization is we have to first understand the problem, draw a picture, what are the unknowns, and then come up with an equation that connects all the variables, and this equation will usually involve some variable that we want to either maximize or minimize. If it has more than one variable, you want to find a relationship and eliminate one of the variables. And then we use calculus, right? You differentiate to find critical numbers and then try to find absolute max and min, which we have a process. We have that closed interval method, check the endpoint, check the critical points. Okay, that's it for this video.